Welcome back, everyone, to the deep dive. You know, when you think about just standing up or running or even just turning your head, it's pretty amazing, isn't it?
It really is. It all comes down to this incredible structure inside us, the human skeleton.
Exactly. And today, we're going deep into that framework, the literal scaffolding that holds us all together.
Yeah, our mission today is more than just quoting that number. Everyone learns, the 206 bones in the average adult.
Right. We want to understand the why, the logic behind it all.
Exactly. It's like looking at the blueprint, how the body is divided into, well, you could think of it as an armored vault and a super dynamic movement system.
Okay, let's unpack that. 206 bones. So there's a main split you mentioned?
Yes, a fundamental division. It organizes everything into two main groups, the axial skeleton
Axial.
and the appendicular skeleton.
Axial and appendicular. Got it. And they have different bone counts.
They do. The axial system, that's your central core. It has 80 bones, and its main job, protection. It runs right down the middle axis of your body.
80 bones for protection. Makes sense. So the axial is the foundation. Then the appendicular must be everything attached to it, the arms, the legs.
Exactly. That's the other 126 bones. And their focus is purely on, well, movement.
Yeah.
Leverage, action, getting around.
So 80 for protection, 126 for movement. That adds up.
What's really quite brilliant about the axial system, those 80 bones, is just how efficiently they protect the really crucial stuff.
Like what? What's it guarding?
Think about it. Your brain and spinal cord, the central nervous system, and then your heart and lungs, the core of your circulatory and respiratory systems, are all housed within that axial structure. It's like nature's armor.
Okay, that's a great way to think about it, armor. So let's dive into that protective core first, section 1, the axial skeleton.
Right. Those 80 bones, we're talking about the skull, a little bone called the hyoid, the rib cage, and of course, the vertebral column, your spine.
Let's start at the very top then, the command center, the skull.
The skull. It's a masterpiece of protection, really, and it's not one solid piece, like you might imagine.
Ugh. I always pictured it as kind of like a helmet, one piece.
Well, it functions like one, but it's actually made of many bones fused together. There are 8 bones that form the cranium.
The cranium, that's the main part covering the brain.
Precisely. The brain box, basically. And then there are another 14 bones that make up the structure of your face.
14 facial bones. Wow. Okay, but instead of just listing them all,
Yeah.
how does that protection actually work? I heard something about sutures, zigzag lines.
Yes. The sutures, they're these interlocking joints where the cranial bones meet.
Why the zigzag, though? Seems complicated.
But that's the genius of it. Those sutures aren't just seams, they're incredibly strong, fixed joints. That interlocking pattern allows the skull to absorb and distribute force from an impact.
Ah, so it flexes slightly instead of just cracking.
Exactly, it spreads the load. And, inside that structure, there's a fascinating bone called the sphenoid bone.
Sphenoid, never heard of it.
It's kind of hidden, but it's crucial. It connects to almost every other bone in the skull. Think of it like the keystone in an arch.
The keystone bone, holding the whole vault together. Cool.
Yeah. And speaking of crucial but tiny, we absolutely have to mention the auditory ossicles.
Auditory hearing bones.
In the ear.
Exactly. 6 of them in total, 3 in each middle ear. They are officially the smallest bones in the human body.
Smallest, what are they called?
You have the malleus, which looks like a hammer, the incus, like an anvil, and the stapes, which is stirrup-shaped.
Hammer, anvil, stirrup, like a tiny blacksmith shop in your ear.
Huh. Pretty much. And believe it or not, these tiny things count toward those 80 axial bones.
Wow. Okay, so back to the face. The 14 facial bones.
Yeah.
Any key ones we should know?
Sure. You've got the zygomatic bones, those are your cheekbones, the lacrimal bones, tiny ones right at the inner corner of your eye socket.
Lacrimal, like tears.
Exactly, near the tear ducts. And then there's the mandible, that's your lower jaw. It's actually the only freely movable bone in the skull, apart from the ossicles, and it's one single strong bone, jawbone.
Right.
And you mentioned one other single bone, the hyoid.
Ah, yes, the hyoid. It's unique. It's this U-shaped bone located in your throat, sort of below the mandible.
What's unique about it?
It's the only bone in the entire body that doesn't directly connect or articulate with any other bone.
It floats.
It's anchored by muscles and ligaments. Yeah. It plays a really vital role in supporting your tongue and allowing you to speak and swallow. Kind of cool, huh?
Very cool. Okay,
Yeah.
so skull, ossicles, hyoid. What's next in the axial tour? Moving down.
Moving down, we hit the shield, the thoracic cage, your rib cage.
Right. protecting the heart and lungs. Seems pretty straightforward, like a barrel of ribs.
Well, yes, it forms a protective cage, but it's also designed for flexibility. Think about breathing. That cage needs to expand and contract.
Ah, good point. So it's not totally rigid.
Not at all. And the way the ribs are set up reflects that. There are 12 pair,
12 pairs, okay.
but they aren't all the same. The first 7 pairs are called true ribs
True ribs, why true?
because they connect directly to the sternum, your breastbone at the front, via their own piece of cartilage. Solid connection, maximum protection for what's behind them.
Okay, pairs 1 through 7. What about the rest?
Pairs 8, 9, and 10 are false ribs. They don't connect directly to the sternum. Instead, their cartilage joins up with the cartilage of the rib above them. So an indirect connection.
A shared connection. Makes sense. Bit more flexible, maybe.
A little bit, yeah. But then you get the really interesting ones, pairs 11 and 12. The floating ribs.
Floating. Why floating?
Because they don't attach to the sternum at the front at all. They only connect to the spine at the back.
No front attachment. Why would you want that? Seems less protective.
But it gives you crucial flexibility. Think about bending to the side or twisting or taking a really deep breath. That space allows your diaphragm to move fully and your lower rib cage to expand without restriction. It's a trade-off, slightly less frontal protection down low, but much better mobility and breathing capacity.
Wow. Okay, that's clever design. True, false, and floating. Got it. And they all connect at the back to the spine, and most connect at the front to the sternum.
Exactly. The sternum, or breastbone, is that flat bone right in the center of your chest. And it's actually in 3 parts itself.
3 parts.
Yeah. The top part is the manubrium, kind of shield-shaped. The middle largest part is the body. And the little pointy bit at the very bottom is the xiphoid process. It starts as cartilage and often hardens into bone later in life.
Manubrium body xiphoid process.
Okay, so that completes the thoracic cage. Skull, hyoid, ribs, sternum.
Huh?
What's left? The axial 80.
Has to be the big one running down the back. The spine.
You've got it. The vertebral column, the central support pillar. It protects that delicate spinal cord and supports pretty much everything above it. It's made up of 26 individual bones, the vertebrae.
26. Okay, but I feel like the spine isn't uniform, right? It curves, and some parts seem chunkier than others.
Absolutely right. The load bearing changes dramatically as you go down. We divide it into sections.
Sections, okay.
Up top, in your neck, you have the cervical spine. That's 7 vertebrae, C1 to C7. They're relatively small and designed for flexibility, letting you turn and tilt your head. C1 and C2 are actually highly specialized for that rotation.
Cervical, C1 to C7. Neck flexibility. Makes sense. Below that.
Then comes the thoracic spine. 12 vertebrae, T1 to T12. These are larger, and each one connects to a pair of ribs. Remember the rib cage?
Right. They anchor the ribs at the back, so less flexible than the neck.
Definitely less flexible. More about stability and forming that protective cage. But then, below the thoracic section, you get to the lumbar spine, L1 to L5, the lower back.
Lumbar. L1 to L5. I feel like I hear about lumbar problems a lot. Is this the powerhouse section?
It absolutely is. These 5 vertebrae are the largest and strongest in the entire spine.
Why so big and strong there?
Think about the mechanics. They have to support the weight of your entire upper body, head, arms, torso, plus any extra load you carry. So biomechanically, they handle the most compressive force.
Oh, okay, so they need to be built tough, bigger, wider.
Exactly. Their vertebral bodies, the main thick part of the vertebra, are significantly larger to handle and distribute all that weight and pressure.
Makes sense. But how does the spine move at all with all these stacked bones? Isn't it rigid?
Great question. That's where the intervertebral discs come in.
The discs. Heard of those too. Usually when they slip or herniate.
Right. They sit between each vertebra, and they're made of tough fibrocartilage with a gel-like center. They act like shock absorbers.
Shock absorbers and cushions.
Exactly. They cushion the impact between the bones, prevent them from grinding together, and, importantly, they allow for movement bending, twisting. They give the spine its flexibility.
So without the discs, we'd be ramrod straight and feeling every jolt.
Pretty much, yeah. They're essential.
Okay, so cervical, thoracic, lumbar. Are we at the bottom yet?
Almost. Below the lumbar vertebrae is the sacrum. In adults, it looks like one big triangular bone, but it's actually formed from 5 vertebrae that fuse together during development. It connects the spine to the pelvis.
The sacrum, fused for strength at the base.
And right at the very bottom, the final piece is the coccyx, your tailbone. That's usually formed from 3 to 5 tiny fused vertebrae.
The tailbone. Okay, and that makes 26 vertebral bones in total, even though some are fused?
Correct. So skull, 22 bones, counting cranium and face. Those 6 tiny ossicles, the 1 hyoid, the sternum 1, the ribs, 24. And the vertebral column, 26 pieces, 7 plus 12 plus 5 plus sacrum plus coccyx. Add that up.
Carry the 1, that's 80. The axial skeleton, the protective core.
You got it. Armor plating complete.
Okay, so core protected, brain safe, spine supported. Now, how do we actually do anything? How do we move? That must be the other system.
That's the appendicular skeleton, the action system. All 126 bones designed for movement. And incidentally, they also form girdles that help protect some organs of digestion, excretion, and reproduction down low.
126 bones for action. Okay, where do we start? Upper body, arms and shoulders.
Sounds good. Let's look at the upper extremities. It all hangs off the pectoral girdle.
Pectoral girdle, chest girdle. What's that made of?
It's basically your shoulder setup. It consists of the clavicle, that's your collarbone, the S-shaped bone at the front,
Collarbone. Easy to feel. Okay.
and the scapula. That's your shoulder blade, the flat triangular bone on your back.
Scapula, shoulder blade.
Right.
So those two form the girdle.
Yep. And this girdle is designed for maximum mobility. Think about all the ways you can move your arm. That comes from the flexibility here, but there's a trade-off.
Trade-off. Less stability.
Exactly. Compared to the hip joint, the shoulder joint is much less stable, which is why shoulder dislocations are relatively common. High mobility often means lower stability.
Makes sense. Okay, so girdle connects the arm to the axial skeleton. What about the arm itself?
Moving down the arm, the upper arm has just one bone. The humerus. Big, long bone.
Humerus, okay. Then the forearm. Looks like there are 2 bones there.
There are. This is where it gets interesting for movement, especially rotation. You have the radius and the ulna.
Radius and ulna, which is which?
If you hold your palm facing forwards, the radius is on the thumb side, the lateral side. The ulna is on the pinky finger side, the medial side. The ulna is generally a bit larger, especially up near the elbow.
Okay, radius on thumb side, ulna on pinky side. Why 2? Why not just one strong bone?
Because of how they work together. The ulna forms the main stable hinge joint at your elbow, think bending your arm, but the radius is designed to pivot around the ulna.
Pivot, like twisting.
Exactly. That crossing motion of the radius over the ulna is what allows you to turn your palm up supination and turn it down pronation. Try turning a key or waving. That's the radius doing its magic.
Oh, okay, so the ulna is for the hinge, the radius is for the twist. Clever.
Very clever design. And that leads us down into the hand. So much complexity in such a small space.
Yeah, the hands and wrists. Feels like a million tiny bones in there. How many, actually?
Close. 27 bones in each hand and wrist combined.
27. Okay, break it down. The wrist part first.
Right. The wrist is made up of 8 small bones called the carpals. They're arranged in 2 rows.
8 carpals. Why so many small ones?
They act kind of like ball bearings. Their shape and arrangement allow for a lot of flexibility and gliding movements in the wrist, letting you bend it in multiple directions.
Okay, carpals for wrist flexibility. Then the main part of the hand.
That's formed by the 5 metacarpals. These are the longer bones that make up your palm. They run from the wrist bones out to the knuckles. They provide the structural framework.
5 metacarpals. 1 for each finger and thumb base.
Oh, got it.
And then the fingers themselves.
Those are the phalanges. We have 14 phalanges in each hand.
14. How does that work with 5 digits?
Your thumb only has 2 phalanges, a proximal one, closer to the palm, and a distal one, the tip. But each of your 4 fingers has 3 phalanges, proximal, middle, and distal.
2 for the thumb, 3 for each finger. 2 plus 2 4 to 3 equals 14. Math checks out.
Exactly. And those multiple joints in the fingers are what give us our incredible dexterity and the ability to grip things so precisely. That opposable thumb is key too, of course.
Amazing. Carpals, metacarpals, phalanges. That's the hand. Okay, deep breath. That's the whole upper appendicular system, right? Girdle, arm, hand.
That's the upper limbs covered, ready to move to the lower half, the ground game.
Let's do it. Lower extremities. Starts with the hips, I assume. The pelvic girdle.
Correct. The pelvic girdle is the foundation for the lower limbs. Unlike the mobile pectoral girdle, this one is all about strength and stability.
Makes sense. It carries all the upper body weight. What bones make it up? It looks like one big bowl.
It functions like one, but it's actually formed from 3 main bones fused together on each side. You have the ilium, that's the big blade-shaped part you feel on your hips.
Ilium. Okay.
But then the ischium, that's the lower back part, the part you sit on, basically, your sit bones.
Ischium. Got it. And the front.
That's the pubis, the most anterior part. The 2 pubic bones meet in the middle at the front.
Ilium, ischium, pubis, fused together for super stability.
Exactly. Load transfer from the spine down to the legs. That's its job.
And there's a big socket in there, right? For the leg bone.
Yes, a really important feature is the acetabulum. It's this deep, cup-shaped socket on the side of the pelvis, formed where the ilium, ischium, and pubis meet.
Acetabulum. And that's where the leg connects.
Precisely. It articulates with the head of the femur, the thigh bone, to form the hip joint, a very strong and stable ball and socket joint.
Okay. And you mentioned the pubic bones meet at the front. Is that a solid fusion?
Not quite solid. They're joined by a piece of fibrocartilage called the pubic symphysis.
Pubic symphysis. So a little bit of give there.
A tiny amount, yes. It allows for some flexibility, which is particularly important, for example, during childbirth.
Ah, right.
Yeah.
Okay, stable pelvis, deep hip socket. Now, for the leg itself, you mentioned the femur.
Yes. The big gun, the femur. Your thigh bone.
How big are we talking?
It is the longest, heaviest, and strongest bone in your entire body.
Longest, heaviest, any strongest. Wow. Why so robust?
It has to withstand enormous forces during walking, running, jumping. All your body weight plus dynamic forces gets channeled through the femurs.
Makes total sense. Okay, femur and the thigh. Then we get to the knee. That seems like a complicated joint.
Oh, the knee is incredibly complex. It involves the bottom end of the femur, the top end of the tibia, your main shin bone, and the patella, your kneecap.
Patella, kneecap, sits out front. And the tibia is the bigger lower leg bone.
Yes, the tibia is the larger weight-bearing bone on the medial inner side of your lower leg. The shin bone. There's also the fibula, a thinner bone on the lateral outer side, but it doesn't articulate directly at the knee joint itself in the same way.
Okay, femur, tibia, patella make the main joint. But knees seem prone to injury.
Oh.
Ligaments, right?
Exactly. The bones provide the structure, but the ligaments provide the stability. This is where it gets really interesting, biomechanically.
Tell me more. The famous ACL.
Yes. You have the cruciate ligaments, which are inside the knee joint. They cross over each other, hence cruciate. There's the anterior cruciate ligament, ACL.
Heard of that one. Often injured in sports.
Very common, unfortunately. It prevents the tibia from sliding too far forward relative to the femur. And then there's the posterior cruciate ligament, PCL, which prevents the tibia from sliding too far backward.
ACL stops forward slide. PCL stops backward slide. Inside the knee. Okay. What else holds it together?
You also have the collateral ligaments, which are on the sides of the knee, the medial collateral ligament, MCL, on the inner side,
MCL, inner side.
and the lateral collateral ligament, LCL, on the outer side. These prevent the knee from buckling sideways.
MCL and LCL for side-to-side stability.
Wow. It's like it's held together with high-tech straps.
It really is an intricate balance of bony structure and soft tissue restraints, designed for both weight-bearing and controlled motion. Incredible. Okay, so below the knee, we have the lower leg. You mentioned the tibia and fibula.
Right. The tibia is the big one, the main weight bearer, your shin.
Yeah.
The fibula runs alongside it on the outside. It's much thinner.
Does the fibula bear weight too?
Not significantly, no. Its main roles are for muscle attachment and helping to stabilize the ankle joint at its lower end.
Okay, tibia for weight, fibula for ankle stability and muscles. Got it.
Yeah.
Which brings us down to the end of the line, ankles and feet.
Exactly. The anchors. Similar structure to the hand, but built for support and propulsion rather than fine manipulation.
So wrist had carpals. Ankle has.
Tarsals. There are 7 tarsal bones making up the ankle and the back part of the foot, including the big heel bone, the calcaneus.
7 tarsals, okay. Then the main foot part, palm had metacarpals.
Foot has metatarsals. 5 long bones forming the arch and main body of the foot, running from the tarsals to the toes.
5 metatarsals, makes sense. And fingers had phalanges. Toes have.
Phalanges too, same name. And just like the hand, there are 14 phalanges in each foot. 2 for the big toe and 3 for each of the other 4 toes.
7 tarsals, 5 metatarsals, 14 phalanges, 26 bones per foot. Wow.
Yep. But the really key thing about the foot isn't just the number of bones, it's how the tarsals and metatarsals are arranged to form arches.
Arches, like the arch of the foot.
Exactly. You have a medial longitudinal arch, a lateral longitudinal arch, and a transverse arch. These aren't rigid structures. They're springy.
Springy, why?
Shock absorption. When you walk or run, those arches compress slightly, absorbing the impact, and then they recoil, returning energy to help propel you forward. It makes locomotion much more efficient and less jarring. It's not just a flat platform, it's a dynamic suspension system.
A suspension system. That's a great way to think about it. Wow. Okay, so that's 126 bones. Did we cover them all? Girdles, arms, hands, legs, feet.
We did. From the pectoral girdle down to the tips of your toes, that's the appendicular skeleton.
Incredible. So just to recap this whole journey, we started with the axial skeleton, that central 80-bone fortress protecting the brain, spinal cord, heart,
Same as
lungs.
the stable core.
Then we moved to the appendicular skeleton, the 126 bones attached to that core,
Mhm.
designed for movement, arms for reaching and gripping, legs for standing and moving us around.
Right. Exactly. The whole 206 bone structure is this beautifully integrated system where the stability of the axial part allows the mobility of the appendicular part.
So what this all really means then,
Yeah.
it's not just a list of bones, is it? It's about how they fit together, how they function.
Absolutely. The skeleton is a masterpiece of biomechanical engineering. Think about the specialized parts, the sutures in the skull, the shock-absorbing discs in the spine, the way the radius rotates, the stability of the pelvis, the spring in your foot's arch.
Yeah.
Each structure is optimized for its job, balancing protection, support, and movement. It all has to work together perfectly.
It really makes you appreciate how complex yet efficient the whole thing is,
Mhm.
especially that transition zone
Yeah.
where the stable part meets the moving part.
Right. And that actually leads perfectly into a final thought for everyone listening to maybe chew on a bit.
Ooh, a provocative thought. Lay it on us.
Okay, think about this. We talked about how the lumbar vertebrae are the strongest in the spine, right where the biggest load is carried axially.
L1 to L5, the heavy lifters.
And we said the femur is the strongest bone in the whole body, the start of the appendicular powerhouse for movement.
Right. The thigh bone.
Notice where they are. The strongest part of the axial column, the lumbar spine, connects directly via the pelvis to the strongest bone of the appendicular system, the femur, at the hip joint. That transition point handles immense forces.
The point where stability transfers into motion.
Exactly. So the question to ponder is, how is that specific junction, lumbar spine, sacrum, pelvis, femur, biomechanically optimized? How does the way those incredibly strong structures are designed and connected allow the rigid support of the axiosystem to translate into the powerful, efficient movement generated by the appendicular system? Think about that connection next time you stand up or jump or even just walk. How does that power transfer really work?
Wow. The ultimate connection point. That is definitely something to think about. A fantastic journey through our own internal architecture.